This is a presentation of a tensile testing lab experiment performed at Arizona State University as part of MSE 421 Physical Metallurgy Lab.
The objectives of this lab are to demonstrate how mechanical properties of metals and alloys are tested for strength, to analyze relationships of stress and strain, to determine the difference between engineering stress-strain and true stress-strain, and to observe differences in mechanical properties for several different metals.
Here are some important definitions. An extensometer is a tool that measures the elongation in the elastic region. A caliper is a tool that measures the initial and final sample dimensions with much better accuracy than a standard ruler. And the gauge length is the distance between two clearly marked points on the test sample.
Stress is defined as the force per unit area and measured in SI units of newtons per meter squared or pascals. In the equation below, stress is represented by the Greek letter sigma, the force is represented by F, and the unit area is A. Strain is defined as the change in length divided by the original length, which is measured in dimensionless units of meters per meter in SI. In the formula below, strain is represented by the Greek letter epsilon, and L represents the length. Finally, stress and strain are directly related in the elastic region, given by the formula below, sigma equals E times epsilon, where E is Young's modulus or the modulus of elasticity.
This is the typical stress-strain curve for a ductile material. The engineering strain, defined as percent elongation from the original gauge length, is on the x-axis, and the engineering stress, defined as the applied force divided by the initial sample cross-sectional area, is on the y-axis. Young's modulus is the slope of the curve in the elastic region, defined as the linear portion of the curve before the yield point. The yield point is the point of intersection between the curve and a line with the same slope as Young's modulus, with an x-axis intercept of 0.2% or 0.002. The ultimate tensile strength is the point on the curve with maximum stress. The fracture point is the last point on the curve at maximum strain.
There are three main regions of the stress-strain curve. The elastic region of the stress-strain curve is characterized by a straight line in which the stress increases linearly with the strain. Physically, this is the elastic stretching of atomic bonds within the material, because atomic bonds are best approximated as a spring between atoms. If the force is released while the strain is within the elastic region, the sample will return to its original length. In the plastic region, the bonds have permanently deformed and slit planes are activated. If the force is released while the strain is within the plastic region, the sample will not return to its original length. Instead, it will return to a strain connected to the point in the plastic region with a line having the same slope as the Young's modulus line. Lastly, after the sample has reached its ultimate strength, it begins to neck, meaning that the gauge diameter is noticeably less than the original diameter.
Now we will discuss the difference between engineering and true stress-strain. Engineering stress and strain uses a static measurement of initial cross-sectional area. However, as the material necks, the gauge cross-sectional area is decreasing. So one must update the stress in real time using the current area. Because the volume remains constant, as the cross-sectional area reduces, the sample lengthens. So the true stress is equal to the engineering stress times the quantity 1 plus the engineering strain, and the true strain is the natural log of the quantity 1 plus the engineering strain.
We see here the difference between engineering and true stress and strain. As the material necks, its cross-sectional area decreases. Although the applied force is the same in both types of stresses, the lower cross-sectional area ends up increasing the true stress over the engineering stress. The stress on the material is effectively increased at this contracted point.
Here are the design specifications for a standard tensile testing sample. This one is a dog bone design seen commonly in ASTM standards with a circular cross-section. The ends are threaded, so they may easily be screwed into the tensile testing machine grips.
Sample preparation. Using sandpaper, taper the center of the sample such that its thickness is reduced by about 0.5 millimeter. We reduce the thickness in the center of the sample so that it fails there instead of at the ends. Next, mark a 2-inch gauge length on the sample. Measure cross-sectional diameter with calipers. Calculate the cross-sectional area. Note to use the multiple average measurements for calculations. The sample is now ready to be tested.
On the left is the tensile test machine we used for this experiment. The image on the right is a magnified view of the sample holder. The yellow arrows indicate the direction of tensile forces being applied to the apparatus.
The applied force is measured by the machine, and its extensometer measures the amount of elongation in the sample. Here we see the graph of data collection in real time.
The image on the top left represents a sample that wasn't tapered in the center. As a result, the sample fractured outside of the gauge length. The sample on the bottom was prepared properly. The video at right was of a 1090 steel sample being tested.
For the data analysis, convert the measurements of load and elongation to engineering stress and strain and true stress and strain using the conversion formulas previously given. Plot the following: load versus elongation, engineering stress versus engineering strain, and true stress versus true strain. Repeat the steps for all tested samples.
Continuing for the data analysis, because thousands of points are output by the lab setup, analysis of this data should be performed by a computational math engine such as Excel or MATLAB. In this experiment, MATLAB was used as shown in the following plots. This is a load versus extension plot for 1090 steel. These values were obtained directly from the experimental setup. Note that the load is in kilonewtons and the extension is in millimeters. Using the measured initial gauge length and cross-sectional area, we can convert load versus extension into engineering stress versus strain. Note that the stress is now given in gigapascals and the strain is given in dimensionless units and not as a percent. Using the formulas provided previously, we can convert engineering stress and strain to true stress and strain. The plot here has few differences with the original engineering stress and strain curve.
Important parameters. Young's modulus is calculated as the slope of the linear elastic region shown here by the green triangle. The yield stress is the point where a line with the slope of Young's modulus and starting at 0.002 on the strain axis intersects the curve. It is the point where the material starts departing from the elastic stretching. The ultimate stress point is the maximum amount of stress the material can withstand. The fracture point is the point at which the material fails. If you draw another line parallel to the Young's modulus from the fracture point, the intersection with the x-axis tells you the percent elongation of the sample at fracture. By integrating the area under this closed loop and dividing by the initial sample volume, you obtain the material's modulus of toughness.
Here are some sample values as calculated from the experimental data for 1090 steel. The Young's modulus was 436.49 GPa. The yield stress was 749.8 MPa. The ultimate stress was 984.8 MPa. The ductility was 3.4%, and the modulus of toughness was 33.8 MPa. By comparing these values with different materials, conclusions can be drawn regarding different material strengths and ductility. This concludes our video presentation. Hopefully you know more about how to calculate these values and important parameters. Thanks for watching.